Okay, my pleasure to be here. Thanks a lot for the invitation. I think this is amazing. I will try to tell my dean to try to copy, because I think this is a great idea that you got many years ago to encourage all what you do in physics. And for me, it's a pleasure to be here, and thanks a lot for giving me the opportunity to talk to you about gravitational waves. As you know, about more than 400 years ago, Galileo marked the initial, I would say, of the birth of the new astronomy, and we, the scientists of LIGO and Virgo, marked the beginning of a new era in astronomy, the 14th of September of 2015, with the observation of the first gravitational wave. And this was possible thanks to these cathedrals of science. This is a laser interferometer gravitational wave observatory. In particular, this corresponds to LIGO Hanford. And you can see these detectors have an L shape with arms of several kilometers. You also have other cathedrals of science here in this island, but this for me is mine. And we were able to detect the gravitational waves for the first time thanks to this, and also thanks that in a faraway galaxy there were two black holes that have been dancing for millions and millions of years, and at the end they merged and they emitted a huge amount of energy, of gravitational radiation, that traveled 1,300 million years until that wavefront reached the Earth. And on that day in September, a Monday, where I was start teaching on that particular day, the Earth vibrated. This is an exaggeration, as it has done many times before and many times afterwards, but with the peculiarity that on that particular day, for the first time, we were having these interferometers sensitive enough, able to detect gravitational waves. This was the signal that was seen simultaneously by the two LIGO detectors, LIGO Livingston in Louisiana and LIGO Hanford, that are separated 3,000 kilometers apart. And the signal, for me this is beautiful, I see it completely clear, you might not, but my eyes do, that lasted less than 0.2 seconds, that was seen simultaneously in both. And to my eyes, I clearly see that this corresponds to the merger of two black holes, and on top, quite more massive. And this happened exactly a century after Professor Einstein presented his theory of general relativity. These results were published as a cover in Physics Review Letters, and this corresponds to the first direct detection of gravitational waves and the first observation of a binary black hole merger. Some other facts is that not only was the first observation of binary black hole mergers, but also the discovery of stellar mass black holes with masses higher than 30 solar masses, that when they merge they form a black hole with stellar mass black hole with masses higher than 60 solar masses. It allowed to do the first strong field test of general relativity. And some other facts is that the speed of the black holes before merger was more than half the speed of light, and the strain, the amplitude of the signal, just keep this number here, says 10 to the minus 21. I will come to that later. This particular signal allows us to open a new window onto the universe, because as you know, in the history of astronomy, every time that we have opened a new band in the electromagnetic spectrum, there have been major discoveries. And gravitational wave is not another new band. It's a completely new spectrum that have properties completely different and complementarity to light. In particular, we are talking about distortions of the space-time itself, not in the space-time, propagating basically at the speed of gravity, at the speed of light. They are generated by the accelerated masses, accelerated energy. So generated by this coherent motion of masses, not by the vibrations of electrons in atoms. Basically, gravitational waves are immune to scattering, obscuration, or absorption, but they are not immune to gravitational lensing. And the detectors, different as the electromagnetic detectors, they basically behave like rulers instead of as buckets. Basically meaning that the amplitude, the sensitivity, is the sensitivity to the amplitude instead of to the power. So, with gravitational waves, this is going to offer a possibility to probe some of the most extreme systems in the universe. For example, the merging of black holes, the merging of neutron stars, supernovae, etc. Now, let's go to the beginning. So what are gravitational waves? So according to general relativity, gravity is not a force. I'm sorry, this is what I was explaining to you. But it is actually related to the curvature of a space-time. Somehow, matter tells the space how to curve, and the space tells matter how to move. Now the question is, when I have matter that moves, when I have objects that are moving around, then the curvature of the space-time has to adapt to the position of the objects. And it takes time for the space-time to react, as the information can only propagate at most with the speed of light. And this produces some perturbations on the fabric of space-times. These ripples are these gravitational waves that then get emitted at the speed of light, carrying information with what have generated them. Basically, the effect of gravitational waves is to change the distance between free-falling test masses. It has some similarities with light because it's a transverse wave, and these are and has two polarizations. And here we have the plus and the cross one, and if it travels in this direction, this is basically the kind of deformations that these gravitational waves produce at a frequency that depend on the kind of objects that they are generating it. In principle, gravitational waves could exist at any frequency, and the frequency in which they had emitted depend on the mass of the objects and how compact they are. If you have, or if you consider more massive objects, they are going to emit at much lower frequencies, and when they are more compact objects, they emit at higher frequencies. Although we could detect them, or they could be emitted at any frequency, I would say that the direct observation of gravitational waves can only happen between 10 to the minus 9 Hertz and 10 to the 11 Hertz. Higher than 10 to the 11 Hertz, we are not aware of any astrophysical objects that could emit gravitational waves. And below 10 to the 9 Hertz, well, you remember, period, frequency, so I have to wait a little too long to measure them. But anyway, the rest of my talk I'm going to focus in what I call my high frequency regime, between a few hertz and several kilohertz. This is the window of the ground-based detectors, and the masses that it corresponds are to stellar mass objects. If I'm interested in more massive objects, like the super massive black holes that they are in the center of almost all the galaxies, including ours, then those gravitational waves are going to be emitted at much lower frequencies, and then there will be other ways to measure them. Now, when gravitational waves are emitted, let's say because of a supernova or because of a fusion of black holes, then they distort somehow the space-time. Gravitational waves are emitted in all the directions, and they are making the space-time to tremble like a drum. But when we go far and far away from the source, the signal is going to become weaker and weaker and weaker. And when this reaches Earth, this perturbation that produces is extremely tiny. So tiny that even I'm moving now and I'm producing gravitational waves, and you are also moving, so we will only be able to detect gravitational waves from the most energetic and most catastrophic events in the universe. As I said, mergers of black holes, mergers of neutron stars, when there are explosions like in gamma ray bursts, or in the most violent phenomena that you could imagine, the proper Big Bang itself. And with gravitational waves, we will be able to extract information when the universe was not even 1 second old. Something completely impossible with light, because the universe became transparent to light when it was basically 400,000 years old. So the challenges here are, one, detect the gravitational waves, and second, to try to disentangle all the information that they carry. And why do we want to do that? Well, because by measuring gravitational waves, we will be able to answer, or to help to answer questions in astronomy, fundamental physics, in cosmology. Questions such as, how do black hole forms? If general relativity is the correct description of gravity, how matter behaves, let's say, in the most extreme conditions, like for example in the interior of neutron stars, or what has been the history of this accelerating expansion of the universe, and many more. Maybe it will help us to discover new events, because in traditional electromagnetic astronomy, every time that we have opened a new band, there have been major discoveries. So there might be things that I have not yet thought about it that we might be able to discover. Now, the question is, in Earth, how large are these effects? How large is this stretching and squeezing of the space-time? So for that, I have to put like a reasonable example in order to convey you that to detect gravitational waves is technologically staggering. So let's put an example of something powerful, energetic, like the merger of two neutron stars. Now, a merger of two neutron stars happens, let's say, once every 10,000 years in a galaxy like ours. So I have to consider that I'm going to put this system in a distance a bit far away, not too far away, but in a not far away galaxy, let's say at a distance of 100 million light years from Earth. So, with such an energetic event, when this signal will reach Earth, what it's going to do is to produce a distortions of 1 part in 10 to the 22. And these are the strong ones. So since this has many zeros, no, you are very smart, you are a physicist, or you will become physicist, let me translate this number. So, with 1 part on 10 to the 22, let me consider the distance between the Sun and Saturn, and I have then the very strong signal coming. That will make that the Sun and the Saturn are going to approach and get closer and far away from each other, a distance equivalent to the size of the atom of hydrogen. And of course, I want to measure then on Earth with detectors that are most have arm lengths of several kilometers. So I would need to design or to construct instruments able to detect disturbances of smaller than 10 to the minus 18 meters, smaller than 1,000th of the time of a proton. So there have been several different ways to attack this problem. The first one was in the late 60s by Joseph Weber. He was the first one that he thought about the problem, and this was the first type of detectors. First type of detectors were resonant bar detectors, and then at the end he published that he has detected gravitational waves. I think it was in 1969, the year I was born. And well, he basically initiated the field of observational gravitational wave astronomy. He was proved to be wrong, but the field started, and there was a full network of these kind of detectors worldwide, initially 18, and then several ones that became quite much more sensitive, but this technology was having some limitations. Basically, at the same time that Weber was constructing his bar, making measurements, there were other people thinking of alternative ways to detect gravitational waves. Also, thanks that in the 50s, there was discovered laser light, so people start thinking like using interferometers would be a possibility, and the first one thinking about them were two Russians, Kerhenstein and Pusnov, but actually the one that basically study and develop and make LIGO to be a reality was our also Nobel Prize, Ray Weiss, that he really studied how this works. How this works is that you have a laser light, a beam splitter, etc. And this is again the example. Here we have the laser, the beam splitter. The light is injected in both arms, and how it works is that the light reaches the end mirrors, bounces back, and this is designed in what we call dark fringe, dark ports here, in which the light comes back. You have that they come in that they get destructive, so all the light will go back to where the laser comes. So no photons will be there, but it is a gravitational waves coming. They are going to have the different arms are going to change the longitude, and therefore some photons will escape, and this is what we'll be able to measure. So this is a very simplified example or a scheme of how this works, and we are not talking about science fiction, because now we have second generation of gravitational wave interferometers all around the world. The first initial network was operating between 2002 and 2010. We did not measure a thing. And now is the second generation, the advanced detectors, composed currently of the two LIGOs in the United States with arm length of 4 kilometers. Then there is Virgo in the outskirts of Pisa with arm length of 3 kilometers. Geo 600 in Rute, the outskirts of Hanover. That is called Geo 600 because it has 600 arm lengths. Now there is Kagra in Japan, 3 kilometers. Underground, cryogenics, is already using technology of what we call third generation detectors. Under construction there is LIGO India, and this is basically this full network of these ground-based detectors, that it's very important to have a network. And this is our sensitivities, the current sensitivities of these ground-based detectors, covering these few hertz up to several kilohertz, and there are also some future ones. And this is how this sensitivity compares. This is frequency, and this is the strain sensitivity of pulsar timing array, laser interferometer space antenna, and so on. So it's important to have a network of them, first because they are not operating all the time, so it will be unfortunate that you have detection when nobody is looking. Also because when you have simultaneous detection, increases the detection confidences, and also if the kind of signals we are measuring are transient signals, to have a network of them helps to localize them. Now, before I show you a very simplified scheme. Here I show you other simplified scheme, but with more details, in particular for LIGO, how LIGO works. This is not just a Michelson interferometer, it also, the arms are Fabry-Perot arm cavities where the light bounces back and forth a few hundred times. And this is a dual recycle interferometer. Here, this is my laser, so eventually all the light goes back. And what we have is another mirror here that is the power recycling mirror to inject all the signal back in, and also the few photons that could escape to do the measurement. With the signal recycling mirror, we can also inject them back in. Now, I have mentioned the word lasers. Well, it's not exactly this laser, is not exactly this laser, it's a much powerful laser. I think we now currently are using a bit less than 100 watts. Eventually in the future, we plan to use a 200 watts laser. All the system is in vacuum because, of course, a little piece of dust is going to bother me. So we have 4 plus 4, 8 kilometers of vacuum with a diameter of at least 1 meter. So the volume of vacuum is much larger than one in CERN. Then, everything has to be isolated, and even isolated from Earth. So there is a big investment in active and passive seismic isolation. So there was a beautiful talk before, but we have sensors at LIGO to be able to detect any earthquakes anywhere in the world with an intensity higher than 4. Because when the wave arrives, we have to measure and to counter-arrest, because otherwise we will be detecting the earthquake, not the gravitational waves. Then the mirrors, we want them to be still there. We don't want them to shake, to move. How we achieve that is by suspended pendulums, but not one pendulum, 2 pendulums. At least LIGO uses 4 stages of pendulum. Virgo uses 5, in which some stages are hung with steel suspensions, but the lower ones are with fused silica. There are more details about coating, the mirrors. Oh, the mirrors. The mirror is not exactly the mirror in the bathroom that I'm familiar with. It's a cylinder. In this case, it's a 40 kilograms cylinder. And in the future, are going to be at least of 100 kilograms. And all that for what? Because we want to have the best detectors, the best sensitive detectors. And what we want is we have to fight when we design these instruments so that the sensitivity should be just limited by fundamental noises, not by other noises. And which are these fundamental noises that are going to limit the sensitivity of the detector? Well, there are of different types. The first is quantum noise, because of the statistical nature of light. Of course, this dominates at all the frequencies, but in particular at the higher frequencies. Then in the intermediate region, what bothers us is the thermal noise, so the Brownian motion of, of the mirrors itself and all the suspensions. So that dominates here. And in the lower frequency regime, it's all dominated by what we call the seismic noise. We are on the Earth. There are humans. There are oceans. So we want the sensitivity to be limited by these noises, not by others, of course. There are many technical issues that we have to fight until we reach these kinds of sensitivities. And what we want is that these curves to go as far down as possible. Of course, the wind, earthquakes, storms, geomagnetic fields, cosmic rays, even density fluctuations of the ground of the atmosphere, everything bothers us. Planes flying on top of it, etc. So everything has to be isolated, well understood, and we have to have environmental monitors. Environmental monitors like accelerometers, magnetometers, measures of the wind speed, of humidity, of temperature, of everything. There are, I don't know, hundreds of thousands of channels of that we measure. So it's a kind of multidisciplinary field in that everything matters. And gravitational wave science is basically a big ecosystem. For one side, there is all what is related to the gravitational wave interferometer, to the vacuum system, to the lasers and the optics, to how the detector performs and its stability, and all the control systems that are in place. But also we want to do science. We need to collect the data. There is computing around it. We have to archive. We have to make sure that the data is there intact. And we have to analyze it. We have to analyze by using different kinds of algorithms in order to extract information. And we have to make statistical confidence assessments. We have to do many things because we want, at the end, to do physics and to have also physics and astrophysical interpretations. We want to study the source physical parameters. We want to interpret astrophysically and also make tests of, for example, of GR or multi-messenger astronomy. But we also have not to forget about the future, because we keep developing new things for future instruments, and we are talking about huge collaborations. When I was showing you the different interferometers, basically we are talking about 3 collaborations that we are working like one, and actually at the end of this year, the 3 will be merged in the International Gravitational Wave Network, and this implies a lot of collaboration infrastructure, service, communication, governments, meetings, making the data to the public and having a very nice discipline among all of us. So these advanced detectors have already performed and concluded 4 science runs. The first one started in September 2015 with the first discovery. Then there was a second, a third that stopped with the pandemic, and then the last science run that started in May 23 and just finished less than half a year ago. And these kinds of detectors, what can we measure? Well, the kind of signals we can measure in systems, one of them are continuous gravitational waves coming, for example, from spinning neutron stars in our galaxy, that they emit basically a monochromatic light. Another possibility corresponds to the superposition of many signals, so we could have a stochastic background of gravitational waves of 2 possible origins, cosmologically or astrophysically. What we would like to detect eventually is the cosmological one coming from the Big Bang. And what we have detected so far is just this type of signal, transient short durations coming from the coalescence of binary systems, either from black hole, neutron stars, or the combinations of black holes and neutron stars. And another possibility could be also short signals like bursts coming, for example, core supernova. These are the kind of stellar mass systems that we will be able to detect with these ground-based detectors. Okay, and how can we find these signals? Well, it depends on the kinds of signals. For the ones that we have proper models, like for kind of neutron stars or compact binary mergers, we have very good models. So the optimal filter is match filtering, for which we need extremely well received models of the signals. And for that, we need to compare theoretical predictions, calibrated to numerical simulations, and to search for all possible of these signals in the noise. And this is also my husband, Sasha Husa, working with me. And I see Andres also here, working with us as well. He will talk tomorrow. So in our group, basically, we work on producing waveforms, data analysis, analyzing data, also doing detector characterization. And we are one of the groups, so also the groups here as well, that we are one of the major users of the Spanish Red Española de Supercomputación, both doing these simulations and the parameter estimation and so on. And here you have beautiful pictures of Mare Nostrum 4, not 5, because this is still in the Holy Chapel. Now, we don't work also alone. We are, that clock is frozen, so I have no clue how long I've been talking. We don't work alone. Actually, it's very important to be in collaboration with other observatories, because when many of these catastrophic signal happens, do not only emit gravitational waves, but also other messengers. Other messengers that could be neutrinos or other electromagnetic lights, electromagnetic waves. So we collaborate with other people, with radio, with optical, infrared, X-ray, gamma, because for different kinds of systems, we are going to expect different kinds of signals. And to do multi-messenger astronomy with gravitational waves, we already have done it once, and only once. Actually, we did it in August, 17th of August of 2017, in which we detected gravitational waves together with a gamma ray. So we managed to do this first detection, in which there was a merger of two neutron stars, and pre-merger we detected gravitational waves, and 1.7 seconds later, Fermi detected the GRB. So this was another fantastic event in which there were two neutron stars, again, that have been dancing for millions and millions of years, and they end up merging each other. Before the merger, they do immediate gravitational waves, the gamma ray, and the kilonova. Fantastic. Amazing. So with just one event, this was amazing, because we could localize between LIGO Virgo more or less the position in the sky. This was in the south hemisphere, and that implied we got to wait about 10 hours until it became dark in Chile, and then immediately it was dark in Chile, SWAP managed to spot exactly in which galaxy that have located, and from that moment on, there was not a single instrument on the Earth or on the space not pointing in the same point in the sky, and for some of them, basically for the following 1 year observing this kilonova. This was amazing. There is one paper with 3,000 authors, 70 collaborations. I'm pretty sure I'm co-author of many people here in the Canary Islands, because also there were many things in Canary Islands also following it up. And this was the first and only unambiguous electromagnetic counterpart of gravitational wave source. So it was a short gravitational wave burst detected initially by Fermi, in which we could get all the other information for the also gravitational waves. The host galaxy was precisely discovered, and then all the astronomy community basically contributed. And this is a vivid demonstration that joint observations are much more than the sum of the individual parts. And we learn many things from just a single event. I mean, when you go to the lab, you do a measurements and you, just one measurement, you do disasters. And here with just one event, we were able to say, well, make a precise measurements that both electromagnetic waves and gravitational waves travel at the speed of light. We could associate that short gamma ray bursts are associated to binary neutron star mergers. We could study this kilonova, this radioactive glow of freshly synthesized heavy elements. So basically, in this table that you see here, all this beautiful yellow color is the proportion of the elements that get synthesized by the mergers of neutron stars. Another portion comes from supernova explosions, but that's not enough. So all the gold that we have here on Earth is coming from these mergers of neutron stars. Well, we could also say things about the interior of neutron stars and constrain the reduced masses, so saying a few getting information about the nuclear equation of state. And for just 1 point, we could even do cosmology, because we could do a beautiful measure of the Hubble constant, because we measure very well the distance, and the electromagnetic people can measure very well the redshift, and that is related with with the Hubble constant. And well, we were having a huge error bar with this first measurement, but our most probable value was exactly between the two values that are in tension. So, well, good. So, what has been the impact of gravitational wave so far? Well, it has helped us to understand the nature of black holes. It has helped us to explain how matter behaves under the most extreme conditions in nature, the origin of heavy elements. But of course, there is a long way to go. Still, with LIGO, Virgo, and Cagra, we have not been able to say absolutely anything about how supernova explodes. Who knows? Who knows if soon there is a supernova in our galaxy in this century. We have not said anything about the continuous emission of neutron stars. And with these detectors, we have not said anything about the stochastic background of gravitational waves. There have been many highlights with the different 4 observing runs. For example, with the first 3 ones, I could say, okay, the Hubble I've already mentioned. A few more things is that we now are aware that black holes exist in the pulsational pair instability gap. Also, black holes neutron star system also exist. Also called compact objects exist between 2 and 3 solar masses. So far, all the black holes we have studied behave like K-error bar holes, and every test we have tried to put on general relativity seems that it keeps being valid with our error bars as well. And we also have been able to measure intermediate mass black holes, etc. So let me put some what we call extraordinary events or mysterious events that we have from time to time. So this is one of them. This is the day 2504 of the year 2019, in which we just measure a binary neutron star merger. Nothing peculiar, no electromagnetic counterpart. So neutron stars are stars between 1 and 2 solar masses and radius about 10-15 kilometers. So the masses are consistent with that, the first and the second. And the total mass of the system was 3.4. You'll say nothing extraordinary, except that these are the measures of the total mass of the system, that if we compare with the masses of the system of neutron star pairs in our galaxy, basically this total mass is more than 5 sigma away from the mean of our galactic binary neutron stars. So, and this might indicate that there is a population of short period binary neutron stars that so far has been invisible to all the radio pulsars. Of course, it could also be that one of them is not a neutron star, that one of the two could have been, for example, a black hole. Another one, 140819. We have a body, the big body of 23 solar masses with something of 2.6. Now the question is, what is this? Because this is the lightest black hole or the heaviest neutron star. So this is another system. So we have a little problem here in this low mass that is challenging a bit challenging for standard formation edge scenarios, or maybe representing a new class of compact binary mergers. Another one. This is particular for 2 reasons, the 21, 05, and 19. This was the merger of 85 plus 66 and the product 142. You know, my sums are terrible. Huh? If you sum, the numbers never match, because the difference is what is getting radiated into gravitational waves. So, fantastic. Black hole producing black hole. And producing the first intermediate mass black hole ever seen. Now, the problem is that according to the pair instability of supernova masses, they should not exist when a star dies, should not produce anything, let's say between 50 or 60 and 120 and or 130 solar masses. And well, 66, well, compare. But this one lies exactly in the middle of this mass gap. So this is another problem, or it could be challenging for standard formation scenarios, except if we could explain the existence of these two bodies, or in particular this one, if it was already a second generation of mergers of black holes. The last science run finished at the end of November last year, and this was amazing. It was done in like 3 chunks, A, B, and C. There was 254 significant detection candidates, more than 5,000 low significant ones. Basically, every time we make observations, the alerts are made public. We also publish catalogs, and up to now we have published the catalog up to the O4A. We also got some exceptional events, and the next run of the collaboration is going to happen at the end, we're going to start at the end of this year. In total, with all the science runs, we have published on the results until O4A, but if we added the candidates that are under study, we are basically have almost 400 events detected. And another very interesting thing is that during the O4 run, we were analyzing online the events and basically sending alerts for almost all of them in less than 30 seconds. For whoever is interested, and actually there are people here in the Canary Islands interested in following it up. Extraordinary events for this science run are, for example, 2 of them, this 290523. And again, there was neutron star and something, and again another something that is again in this gap that we will not be expecting objects there. So there is more evidence, apart from the one that I mentioned before, that there are more objects than expected in this lower mass gap. And then, oh, fantastic one, the 231123. This is the two strongest, the strongest signal. Well, the strongest signal, no, but the strongest bodies we have measured the merger, 137 merging with 103 and forming the resulting one of 225. And, well, again, this one, it is again in the upper mass gap. The other one also could be. So basically we are having already at least two systems that it puts us more questions than gives us answers. So up to now, this is the beautiful map of masses of what we have measured. We have measured in black holes all what is in blue, and in this orange the neutron stars. And before, you can see here in red the masses that were inferred from electromagnetic observations. So basically we have discovered a few of completely new populations of black holes with masses higher than 20 solar masses. We have also been filling the gaps, and I just want to point out that in these first 10 years of LIGO Virgo Cargo observation, the black hole detections have suppressed by far the XX black holes observations that have been performed in the last 60 years. About the populations of the black hole, so this is the distribution. So basically you see that this is quite well described with this broken power law, but there have several peaks. So there is a first peak at 10 solar masses, there is this other peak at 35 solar masses, and it seems that here is appearing another peak around 20 solar masses. With gravitational waves we are able to do cosmology, and we can do cosmology what we call bright sirens. So bright means that we got also the telemagnetic counterpart, that we could measure the redshift, because we can measure very well the luminosity distance. But also we can do cosmology with what we call the dark sirens that also contribute. Basically the last interesting event we mentioned, it was mentioned and it was made public last September with the 10 years anniversary, was an event that was actually having very similar masses to the first one. so around the 30 solar masses, each of them that were emerging, with the only difference that this time the detectors have improved a lot. So if this was the first signal that we measure, this was the one of the year of last year. And then we can do fantastic things. And about these fantastic things is that we could prove the Hawking area theorem. So we could also prove that Hawking was right, saying that the area of the remaining black hole horizon was much larger, or was larger, than the sum of the areas of the progenitor. And this is not all. We just have measured up to now compact binary coalescence, but there is going to be many more science. Eventually, we could detect gravitational waves from core collapse supernova. We could detect gravitational waves in connection with neutrinos. I'm studying continuous gravitational waves. I have not seen still a single gravitational wave coming from the neutron stars themselves, but that could be an amazing science, independently that the neutron star is isolated or in a binary system. It's not a binary system. It could even be more exciting because it could be a accreting measure for the companion. And with that, I could study the interior of neutron stars. I could study the nuclear equation of a state, discover exotic states of matter, make more tests on general relativity, and also there are some kind of signals or continuous signals that could be associated with the dark matter sector. But that's just the beginning. We are the beginning of an area. We are just observing the tip of an iceberg. There is many more that we have not yet reached. We want to go much, much farther away. And therefore, both in the US and in Europe, we are thinking ahead. What are the next steps? The next steps is that soon there is going to be LIGO in India, a third detector there. There is Cosmic Explorer eventually that will appear in the US, Einstein Telescope in Europe, and in Einstein Telescope in Europe, either is going to have a triangular shape or there are going to be two locations with an L shape, going to go underground. In the US, they are already thinking of L shape, but much, much larger. US is big, so we are talking about instruments of 20 or 40 kilometers arm lengths. And all for that, for what? Because this is basically our current observations. We want to gain 1 order of magnitude in most of the frequencies. We also want to go to lower frequencies, so here the gain will be several orders of magnitude. 10 years of observation, 400 detections, but with ET and Cosmic Explorer, we are going to do thousands of observations a day, allowing to perform or to measure many weak signals and many more signals. And if up to now, with second generation detector, we can just reach at most redshift 2, with Cosmic Explorer and Einstein Telescope, we will be able to reach at the redshifts 100 for some of the masses. So basically, Cosmic Explorer and Einstein Telescope, they will be able to observe the entire universe of all these mergers of black holes. Also, we will be able to detect with very high signal-to-noise ratio many of these binary neutron stars mergers, not just one, and have them localized and be able to do very exciting science that will allow these electromagnetic counterparts. And for what? Well, because we want to do astrophysics, cosmology, and fundamental physics. We want to study the black hole properties. We want to multi-messenger astronomy. We want to test GR. We want to probe the dark sector. We want to understand the cosmological origin. At the beginning there was inflation, phase transitions, cosmic strings, and of course discover new things. And that's not all. I've just been focused basically my talk about these ground-based detectors, but there are other things coming along. You might have heard about pulsar timing arrays, pulsars, these neutron stars. There are some neutron stars that behave that are the most precise clocks of the universe, and they can be used. And actually, in the summer of 23, the International Pulsar Timing Array and all the other variants, they were able to measure for the first time the stochastic background, I guess astrophysically background of gravitational waves. The LISA, the Laser Interferometer Space Antenna, is already a mission adopted by ESA that will be able to explore the low frequency regime and doing an amazing science. And if you want to do other indirect detection in the low frequencies, well, you can also measure, or you can also study the B modes of the cosmic microwave background. So I'll finish here because they had just told me I have run over time with my summary. So we have been witnessing the birth of a new area in astronomy. The current generation of gravitational wave detectors, I mean, I would say they have already been transformed. They've revolutionized and opened new questions about our current understanding of the universe. We have already completed 4 observing science RAM. We are doing multiple types of searches. I just give you some details, but there are many more studies that are going on. The next generations are around the corner, a decade from now, that they will be amazing. We will be able to do precision gravitational wave astronomy with them. And LISA is going to be the first space mission that is also going to open an entire new window to the universe. And together, LISA, Cosmic Explorer, and ET, operating together, they will be able to do multi-band astronomy as well. So I stop here. Thank you.
Thank you very much, Alicia. Now we have time for about 2 questions, if anyone wants to question. The microphone, if you want. Thank you.
You can ask me in any language, but any no.
Ok. ¿En español?
Sí, puede ser en español,
Okay.
ningún problema.
A partir de las investigaciones que llegaron de las ondas gravitacionales, ¿qué conclusiones podría sacar, por ejemplo, de la existencia del gravitón? ¿O se podría intuir sobre las características que podría tener?
And now should I answer Spanish or English?
Whatever you want.
Bueno, nosotros no solo cuando estudiamos las ondas gravitacionales en cada detección, intentad sacar los parámetros, intentad sacar las masas, los spines, etc. Entonces tú utilizas unos perfiles muy particulares para poder moldear de alguna manera esa señal. Y eso lo puedes hacer con relatividad general o con teorías modificadas, con teorías alternativas. Entonces, uno podría suponer que existiera el gravitón y que el gravitón, por ejemplo, tuviese una cierta masa, y entonces lo que puedes hacer es intentar probar a ver qué ves o qué no ves. Y de momento, todo lo que hemos observado es que todo concuerda con relatividad general y además concuerda que el gravitón, con una barra de error muy grande, es consistente con masa cero. Hasta el momento.
Hola, ¿qué tal? Buenos días. Nada, gracias por la charla. Yo, bueno, no sé si a lo mejor se va un poco fuera del tema, pero leí en una de tus diapositivas que podemos usar la ciencia que se hace con ondas gravitacionales para detectar nubes de acciones, ¿no? Que es
¿Sí?
la partícula esta que está ahora
Sí.
de moda para describir la materia oscura. Si puedes desarrollar un poquito más cómo se hace o cómo...
Vale, entonces si tienes un agujero negro que está en rotación, podría tener una nube de bosones, acciones o demás que esté girando alrededor. Estos son trabajos de Víctor Cardoso y colaboradores. Y entonces allá da una descripción que la señal que entonces eso emitiría sería una señal tipo onda continua, persistente y además monocromática dependiendo de las masas pertinentes. Y entonces con nuestras búsquedas de señales continuas en cualquier dirección del cielo, dado que no hemos visto ninguna, pues también hemos podido poner cuotas, y no siento mucho, si luego quieres tengo más slides en mi ordenador, con detalles, en que pues, se ha podido limitar pues, las masas, las energías de esas posibles acciones, y además se han podido poner upper limits mucho mejor que no de experimentos de partículas dirigidos a ello. Es decir, no solo eso podría ser una manera de materia oscura, hay más. Otro tipo es que la materia oscura, por ejemplo, podría ser primordial black holes, agujeros negros primordiales, y dependiendo si tuviesen, por ejemplo, masas asteroidales, pues también emitirían, y si estuviesen parejitas, también emitirían ondas gravitacionales continuas en nuestra banda de frecuencia. Eso también lo miramos, también hemos podido limitar pues, su abundancia o cuántos puede haber, digamos, o en nuestra galaxia. Y la otra hipótesis, por ejemplo, es que agujeros materia oscura, por ejemplo, podrían ser tipo WIMPs, y estas particulitas, por ejemplo, pueden chocar contra nuestros espejos y les dan un impulso. Entonces, eso no son ondas gravitacionales, pero el impulso es algo que me molesta, porque de alguna manera lo voy a registrar como si fuese una onda continua. Y eso es otra cosa que buscamos, porque el empujoncito que le daría al espejo volvería a hacer oscilar el espejito imitando una señal de este tipo.
O sea que el experimento en realidad tiene, o sea, puede medir otras cosas que no sean ondas gravitacionales o producidas por...
Bueno, te puedo medir resonancias de Schumann, te puedo medir muchas cosas. Y aquí me he centrado en lo que hemos observado en ondas gravitacionales, pero evidentemente de estudios hemos hecho muchos, y si hubiese sido, digamos, la charla para la SEA, habría dado una charla algo distinta, mucho más técnica y poniendo más resultados.
Nada, muchas gracias.